So we'll continue our discussion about data link layer. We've just talked about Ethernet in some detail, and today we'll talk about Wi-Fi. I'm sure you're all excited to learn about this technology which you use every day. So wireless LANs use ideas which are already there in Ethernet LANs, okay, but they have to make modifications to the protocols because some of the ideas in the protocols do not work in wireless settings. So let's look at a wireless local area network. So suppose you have an access point here, and you have, let's say, your laptops. You have two laptops, let's say, which want to communicate. And in this particular setting, of course, let's say both of these are connected to the same AP. So suppose we just say that we are going to use CSMA CD. Okay. So that was already there for so many years in Ethernet, and why not just use the same thing over here? Okay. So let's think about it. Suppose this is A, this is B, and this is C. And let's say that A wanted to communicate to B, and so let's say it does carrier sense. And it doesn't find anything on the channel, so it sends out its frame. Okay, let's say it's transmitting to B. Okay. And is it going to work always? So you know, all these three devices belong to the same local area network. Okay, so I haven't discussed these terms before, LAN and WAN. So really the AN stands for area network in both cases, and LAN stands for local, and L stands for local here, and W stands for wide area. So this is wide. So local area is a term used for a small network where the devices are close to each other within a short distance, physical distance of each other. So you have a few, let's say few tens of devices typically in a local area network, and they are all connected together possibly through a switch, or they are on the same bus. So wide area network is a term used for long distance networks where you could go kilometers or hundreds of kilometers away, you know, and all the machines in this large area would be called a wide area network. Okay, so it's a relative term that people use. But LAN technologies, most of the LANs today would use Ethernet, CSMA, CD, but of course there are other LAN technologies too. Okay. So Wi-Fi is a technology used for wireless LANs. Okay, so getting back to this question, is carrier sense going to work? So suppose you had a system where you had A, B and C on an Ethernet bus, let's say. Now A did carrier sense here, and of course he knew that nobody was transmitting at that instant, and he transmitted. Okay, that's what we said earlier. Okay. And now let's say that over here C wants to also transmit. Okay. So C is also going to do carrier sense, but let's say he starts his carrier sense here, and he's sensing. Now the problem is that this signal from A decays very fast as it goes out. So let's say that this is the signal. Okay, it's really large in amplitude, but by the time it reaches B, it's really small, and by the time it reaches C, it's almost like noise. In amplitude. Okay, so the signal decays very fast. And the reason is that the wireless signal is propagating in all directions, in all three-dimensional directions. And in theory, if you take an omnidirectional antenna, the signal is going to go equally in all directions. Okay? But in practice, maybe you, in a particular application, you will use an antenna which is directional, which sends most of the energy in one particular direction. But still you would expect the decay to be something like 1 over d to the power of alpha, where d is the distance. So the distance from the transmit antenna, and alpha is a parameter which experimentally people find to be something between 2 and 5. Okay? And theoretically, of course, you could say it should be 2, because if you have an antenna here and you're looking at distance d, then the entire energy sent from this is going to be spread so the entire energy would be spread around a sphere with radius d, and you know that the area is 4 pi d square. Okay, so you would expect that it should be d square, but in practice they find in certain settings it's even more than that. It decays faster than d square. Okay, because there are obstacles and so on, and you can have multipath and so on. Okay, causing all sorts of interference, diffraction, and various things like that. So anyway, so wireless engineers come up with these models based on measurements. Okay, so the signal decays very fast by the time it reaches B, but let's say that in this case at least the signal to noise ratio is reasonably good at B, that B can actually detect the signal and make out what was said in that. But let's say by the time it reaches C, it becomes so faint that the signal strength is even less than the noise strength. Okay, so C cannot even hear A at all, A signal at all. So even though he does a carrier sense, he cannot hear, C cannot hear A. So if you're just using plain CSMA, let's say CD, whatever from Ethernet, C would transmit. Let's say he's sending to B, he might do something like that, right? He might, in this case, everybody wants to talk to the access port. So he transmits it over here, and carrier sense failed because C was too far away. What about collision detection? Does it work over here? So we said in CSMA CD, the person who's sending has to listen to the overall energy on the channel, and if the energy increases substantially, then he knows that a collision has occurred. So are A and C going to detect collision? Let's think about that. So C starts transmitting, and A's signal is pretty much like noise. It's not even audible. It increases maybe the energy a little bit, and here too, right? So at this particular point in time, C's signal only adds a little bit to the energy. Okay, so if I think of this as being the total energy or the signal amplitude, So collision detection is not going to work here because the energy has hardly changed. So now we seem to be in a fix that the carrier sense part may not work and the collision detection part also may not work. Okay, so how are we going to deal with this? And clearly there is some solution out there because Wi-Fi does work. But the question is, how are we going to do it if we have to invent something like this? Okay, and so the people who are developing Wi-Fi had to think about this. And the question is, what should we do? Because there are other things you could do. For example, suppose you give each person only a particular frequency to transmit on. Okay, that and different frequencies, are orthogonal to each other, and you can maybe filter out one signal from somebody else. Okay, but that may be an idea. Okay, but it becomes complicated to do that. Who is going to assign frequencies to different devices? Right, that becomes tricky. Okay, so they wanted something which looks very much like Ethernet. And so they actually went for a CSMA protocol, but not with collision detection, because collision detection is not going to work. So carrier sense might work in some situations. So suppose we look at this situation. This is the access point, and let's say this was A, maybe a mobile, and let's say C was here, a laptop. Now if A is transmitting to B, C might be able to do carrier sensing and detect A's transmission because it is nearby. So carrier sense works. So carrier sense is not really a lost cause. So why don't we keep it? Because sometimes at least they'll be able to hear each other and not transmit unnecessarily. But collision detection is going to be very hard to get to work because somebody who's transmitting is transmitting a signal with amplitude so much higher than what he could possibly hear from somebody else. This could, this signal could be orders of magnitude higher than the signal he's getting from some other device. Okay, because the signal is decaying very fast. And like somebody mentioned in the live session, but can you subtract out your own signal? Okay, that's a question that researchers thought about. So suppose A is transmitting a particular signal, and this is what he's transmitting, what I'm drawing here. And let's say that this is what C is transmitting. I'm just going to draw it like this. And by the time it reaches A, it's going to be really small. So I'll just draw it a bit exaggeratedly like this. Okay, something like this. In practice, of course, it's going to be much smaller than that relative to A's signal. And okay, I think I need to draw that a bit differently. Okay. Okay, so this is C's signal, let's say. This one is C's signal. Okay, and this is A's signal. So if he listens to the air, he knows what he is sending, so he could potentially subtract this out. So suppose this is what he is hearing. Okay, from so let's say that you have a circuit which is receiving everything that is heard from the antenna. So this is what he's hearing, A plus C. So why not subtract out my own signal to get what somebody else is transmitting? Okay. So this is something people have worked on in the past, I would say 10-15 years. But it's not easy to do, because the thing is, what you get, what you receive, this is what I'm hearing, this is what I'm receiving, is not exactly what you are transmitting. It might be a little bit off. Okay, so suppose let me maybe make it more explicit. Suppose this is A of t, this is C of t. What I'm transmitting is A of t, but what I receive A is going to receive some, let's say, beta times A of t plus let's say theta times C of t. Okay, so just make it this way. So beta is not exactly equal to 1. Okay, there are some losses in the circuits and so on that you use, and theta is way smaller than 1. Okay, so we are saying that A is transmitting a signal, which this goes, let's say, to, this is what he's transmitting, A of t, and he's transmitting to some, let's say, some antenna, and at the same time he is also receiving something. So this is the receiver circuit, which I am calling Rx. Okay, so what effectively he gets over here is not what he gets over here, let's say, is what I've written here. It's beta times A of t plus theta times C of t. Okay, to simplify it, let's say this is what we are going to get. So even if he subtracts out what he transmitted, okay, so if I take beta times A of t plus theta times C of t, and I subtract out what I transmitted, I am still going to get something like this. And this could still be much larger than this, okay, because theta is extremely small, orders of magnitude less than 1, and beta is a little bit less than 1, just because of all the attenuation in these various circuits and so on. Okay, so it's a non-trivial thing to subtract out your own signal and hear what is there on a wireless channel. It's much easier to do this on a wired channel where theta is close to 1. You get pretty much what the other person is transmitting. Okay. So we've ended up in a situation, in a wireless situation, where when you're transmitting you can't listen, so you become deaf while transmitting. Okay, and that makes it very hard to get carrier collision detection to work in Wi-Fi. So what do we have here? We are going to go ahead with carrier sense we will use. But the question is, how are we going to detect if there are collisions, because they can clearly happen. So how are we going to detect collisions? And in fact, the solution is what we were thinking of earlier. Before we discussed about CSMA CD, we were discussing about acknowledgements. So why not use acknowledgements instead? So suppose you have a setting where you have let's say A, B, C. If A wants to transmit to B, it is going to first do carrier sense for some time, right, till it figures out that the channel is free, and only if it has a frame to send and the channel is free, it will start transmitting. And it has no idea if B has got the frame because it hasn't done collision detection. It can't do any collision detection. So what it is going to do, it's going to hope that B has got it, and B would have to actively reply saying that I got the frame. So this is the data packet and this is the acknowledgement. So once A has got back this acknowledgement, it knows that the frame was received correctly by B. And of course, if it doesn't get this back, then we have to think of something, right? We'd have to do some. We'd have to wait for some time and retransmit. And we'll look at that a little bit later. But if you don't get back an acknowledgement, you would assume that there has been a collision at B. And then you would back off for some amount of time and retransmit. Okay. So if there is no acknowledgement, then we assume that a collision has taken place. So there are other issues which come up too, and one of them is called the hidden terminal problem. And we've actually already just discussed the hidden terminal problem here in this figure. So it's possible that two nodes are so far apart in the wireless LAN that they cannot hear each other. The other signal becomes so faint that it's actually less than the noise. So they won't actually be able to communicate to each other. But in this setting, we see that they don't really want to communicate to each other. They want to communicate to the access point B, who can hear both of them. Okay. So in this situation, we say that A is hidden from C. So we have a situation A B and C, and B can hear both A and C, but A and C cannot hear each other. And this is where they are hidden from each other. So this is called the hidden terminal problem. A and C are hidden from each other. So the problem is that if A transmits, okay, and C transmits, if even one of them starts before the other, they cannot carrier sense each other, and so they will transmit and there will be a collision here. Because both their signals will add up. Okay, and so B will not be able to decipher what either say. Okay. So this is a problem. I mean, how are we going to address this issue? Can we do something about it? Okay, and there is a solution provided in Wi-Fi for this, and essentially the idea is that instead of just sending, in this particular case they would both do carrier sense and then they would send a large frame and the frame would not get through. Can we do something else so that we don't waste so much of time? Okay, so what is going to happen is that A sends a frame to B, right? It does carrier sense, but C might also do carrier sense, and detect that there is nobody transmitting, incorrectly detect that there is nobody transmitting, and transmit a particular frame. Now they don't get any acknowledgements because there's a collision. So they will detect a collision but quite late, because this frame could take a significant amount of time on the channel. And all this time is wasted. So this much time is wasted on the channel. So can we shorten this time in some way? If we could have done collision detection, that would have been perfect. We could have immediately stopped, and that was the advantage of doing collision detection in Ethernet, that you didn't have to wait for very long. You started sending your frame and very quickly you detected that there was a collision and you stopped. Here you can't do that. You wait for a very long time and you just don't get back an acknowledgement. Okay, so you waste a lot of time. So how are we going to solve this problem? We just don't want to wait forever over it. So the solution used by Wi-Fi is something called virtual carrier sensing. So how does this process of virtual carrier sense work? So clearly A and C are not going to hear each other from a carrier sense. So what can we do something better? And you might think, how is it even possible for A to communicate to C that he wants to transmit? And the solution is sort of staring us in the face, in that B is the one who can talk to both of them. So clearly we want B's help a little bit over here. Suppose A wants to talk to B. Maybe instead of sending this full frame, suppose it sends a very short frame. Instead of sending the full data, before sending the data, maybe it sends a very short frame, and it tells B that I have data to send to you. Okay, I have whatever, a full frame of 1500 bytes or whatever to send to you. Can you make sure that everybody who's around you also knows that? Okay, and that is called a request to transmit, request to send. So it's a short frame to tell the receiver that it intends to send. A data frame. So just to be clear, we have A, B and C, and A and C cannot hear each other. So A does carry a sense, and when it has data to send, it will send first an RTS. And everybody has heard this RTS from A. Okay, so let's say that there was somebody here, D. Let's say that there is, okay, this is good enough for us. So everybody hears this RTS who's around A, within hearing distance of A. And they all realize that A wants to send to B. Okay. And now this is not good enough to solve the problem because B has to also cooperate. So B has to announce to all its neighbors that I am going to get data. Okay, so B replies to A with something called a CTS, a clear to send. And the clear to send is a message to A saying that yes, all is well, you can send. It's sort of like an equivalent of an acknowledgement, let's say, to an RTS. But the point is that these are quite small in size. So it's a short frame with just few bits because it doesn't contain any information, data information. It just has to reply to this message. Saying that sender can transmit data. Okay. And how is this going to help? So clearly this has to have some information. So C has to use this information. So C has heard the CTS. But it didn't hear the RTS. So C has heard the RTS, so even when A is transmitting, so obviously A is going to send, let's say, a long data frame over here. C should not try to transmit. Okay? And if C does carrier sense, he will think that the channel is free here. But C has heard the CTS and he knows that somebody is going to transmit to B immediately after the CTS. And this is why we call it virtual carrier sensing. Okay, so C does not transmit here during this period. Okay, so C remains silent even if it has data to send. It has data to send. Yeah, and which is why it is called virtual carrier sensing. Yeah, and of course, how does A know that everything went off well? Because he's going to get an acknowledgement. So he's going to get an acknowledgement from B. Okay. So we are almost done with this idea of virtual carrier sensing, and you might think how long is this going to last, because C cannot hear this, so C cannot hear the data. Okay, he'll be able to hear this ACK finally. Okay, but I mean, how do we work this protocol? So suppose so one thing we could do is we could say that C should just remain silent till he hears this acknowledgement. Okay, that may be one solution that we have. But the problem is, what if B does not send the acknowledgement for some reason? Because there could be bit errors or something over here, because of which B doesn't send an acknowledgement. And if you say that C should wait for till he hears the acknowledgement, he shouldn't transmit anything, C could be waiting forever. Okay, so that's not a clever solution. So let's say that actually this CTS has information about how long this transmission is going to occur. So what we are going to do, we're going to put within this CTS information about how long this is going to be, and it's called the network allocation vector, which is present. This is present in the CTS. Okay. Let me write that down. NAV stands for network allocation vector. So we are making it easy. So we are saying that when B sends out this clear to send, he also says how long he wants all his neighbors to remain silent. Okay, and that NAV is going to contain that information. Okay. Now you might say that how does B know what the NAV is supposed to be? Because he doesn't know the length of this data frame, at least from what I've shown you till now. I mean, the data frame could be anything. There's a maximum frame size, but you don't want everybody to wait for the maximum, right? If the data frame is itself small, then you should tell people that, I'm only going to transmit for a small period of time. But since the data is coming from A to B, how does B know what the NAV should be? Okay, so we go one step back and we say that the RTS itself should have the NAV, and it should tell B for how long the channel is going to be busy, okay, with this particular transmission. So that information is also there. Let's say that, let me draw it in a different color. So there is an NAV given in the RTS, okay, and that's up to here. Okay. So this NAV is being announced in the RTS. So A is telling B, and in fact he's telling everybody around him, because they can all hear this frame, they can all hear the RTS, that I intend to send a data frame, and the whole transmission including the acknowledgement and CTS and everything is going to take this much more time. And B replies, okay, so he removes the time corresponding to the transmission of this CTS, so it sends another NAV which is a little bit less than this corresponding to the CTS, and he tells all his neighbors that the transmission, I am going to be part of a communication and the channel is going to be busy up to this point in time. Okay, so how is this going to help deal completely with the hidden terminal problem? So with the hidden terminal problem, we said what's going to happen is that when one person is transmitting, the other has no idea that he's transmitting because he's too far away, and so he too starts transmitting, and so there's a collision and a lot of time is wasted. So let's see how this solves the problem. So although C could not hear the RTS, let's just write it down again. You have RTS, CTS, data and ACK. So C could not hear this. So C cannot hear both of these. However, it can hear this. So C is going to hear the NAV and it's going to remain silent till here. Okay, so we prevent collision in that way. So we have effectively avoided the collision with this virtual carrier sensing method. Okay. And of course, after this, it can contend for the channel. It can again start doing a carrier sense and so on, and we'll look at those details a little bit later. Okay. So effectively, the CTS is acting. B is sort of helping out in the transmission, and he is sort of announcing that he is going to receive data, and he tells all his neighbors to be silent for a certain amount of time. Okay. So what is the rule over here when we are using RTS CTS? And the answer is that anyone hearing an RTS or CTS should remain silent for the NAV mentioned in it. Okay, so of course C hasn't heard the RTS, it has only heard the CTS, but it remains silent for this much amount of time. So why do we want people who have heard the RTS to remain silent? You might think that because after all the data is going from A to B, and so as long as people around B are not transmitting, things should be fine. The data will be able to reach B. So what I am saying is, in this particular example, D hears the RTS, and so it remains silent. and C here is the CTS, and of course it remains silent for this much amount. So why are we saying according to this rule that D should remain silent all the way from here up to here? Because after all, this data, even if D transmits, he's probably not going to interfere with B. So suppose, let's say D here is the CTS, but didn't hear the CTS from B. So how is, so this is essentially saying that D is so far away from B that even when D is transmitting, he's probably not going to interfere with any signal at B. Okay. But we are saying that D also should be silent. And the answer is there in this figure itself. The thing is that even though if D transmits, he's not going to affect the reception of this data frame by B because he's quite far away. He is going to affect the reception of this acknowledgement from B at A. Okay? So suppose D just ignored the RTS and he just did his own carrier sense somewhere and started transmitting over here. Then if he starts transmitting, he might transmit while this ACK was being sent by B, and then A will not receive the acknowledgement. Okay, so this is the reason we want, since the protocol in Wi-Fi is two-way, the data and an acknowledgement comes back, we want everybody around the sender and the receiver to be silent during that transmission. And this is what the RTS and CTS essentially effectively carry out. Okay, so the rule is that as usual, like in Ethernet, you do carrier sensing. When you get a frame, first you do carrier sensing, then when you get a frame, you send RTS, get CTS, and only if you get a CTS, you start the data. Okay, so suppose A sent an RTS and did not get a CTS, then he's not going to go to the third stage. Okay, but if he gets a CTS, he knows everything is fine, and he starts transmitting. Okay, and once he gets this acknowledgement, he knows that he has been successful. Okay. Okay, so what you have in Wi-Fi is that you have different options. So first option is to not use RTS CTS, and RTS CTS together effectively are called virtual carrier sensing. Okay. This is also allowed, and most of the time the Wi-Fi networks will use this, okay, because they might, while designing this, people will say that suppose there isn't much contention in the network, then this RTS CTS time is wasted. Okay, and so they say we just go into data and ACK. If the data doesn't get through, we can figure out from the acknowledgement, right? And okay, so you don't use RTS and CTS. So in this case, you just do carrier sensing, and then you can send data, and then you get the acknowledgement from the other end. Okay, and if you don't get an acknowledgement, you assume that the frame was lost because of a collision, and then you try to retransmit. And the other option is that you use RTS CTS, and here if you have a frame to send, you do carrier sense first, and then you send RTS, and then you get back a CTS, and then you send your data and get an ACK. Okay, so you try to retransmit if there is no ACK, and that is there in this case too. Okay, so you might think, why don't people anyway put RTS in CTS, because it uses just a small amount of time compared to this. So it turns out that actually that in practice that RTS and CTS may take longer time than I've shown in a diagram like this. And the reason is that you want RTS and CTS to be heard by lots of people. Okay, so I mean, the more people you keep silent around you, the better for your transition, the less chance of getting a collision. So how do you make sure that somebody hears a frame that you send out, hears it better, right? Or I said here, more people hear it and so on. So you studied that in the physical layer, that if you use a lower modulation rate, if for example you use BPSK rather than QAM16 or QAM64 or whatever, then the signal to noise ratio is better. Okay, you're sending the signal at the same power, but you're using a lower modulation rate. So effectively the SNR is higher. So in practice, the RTS and CTS are usually sent with lower modulation rates. And hence their duration. So even though the number of bits in an RTS may be small, their duration can be much larger than you would expect. Okay, so what it might look like in practice is that RTS, CTS, these are sent by BPSK. Okay, just to ensure that the signal to noise ratio is high. And then you have a lot of data to send, so you would blast it out, let's say with a high modulation rate. You want it to go as fast as possible. Let's say it's QAM 256, let's say. Okay. And the power that you're using is the same, the energy that you're sending per unit time is the same. Okay, but here each bit duration is much longer than it is here, effectively. Okay, so and then you get back the ACK. Okay, so the duration can be substantial, comparable to the data transmission. So people found that when they actually sent RTS and CTS, though these were small in number of bits compared to the data, because the data was sent at a much higher modulation rate, the duration of the data became comparable to these RTS CTS frames. Okay, and so people usually switch this off and go with the first option. Okay, so here too I need to mention that if you don't hear CTS, then you assume that there was a collision. Okay, and so what you do is you try to retransmit later. Okay, and we'll talk about the exact retransmission mechanism in the next class. Okay, but it's essentially you're going to use some sort of exponential backoff, right? Because you don't know how many people are colliding, and the exponential backoff lets you quickly sort of relax the channel so that somebody gets a chance to transmit. Okay, so we'll discuss other issues in Wi-Fi in the next class.